We're going to talk about the combined gas law. You need to be able to convert between units of temperature and pressure to determine the relationship between all three temperatures, pressures, and volumes, which you find on table T. They give you the pressure, volume, and temperature of the first gas versus when you do it again for a final condition. So the first side is the initial conditions, and the second side is the final conditions. Some important rules: they need to be in Kelvin, because you don't want to avoid zeros and negative values. You have to have the same units for both volumes and pressures on each side. So if the volume says milliliters on the left, it needs to say milliliters on the right. If it says a pressure in kilopascals on the left, it needs to say the same kilopascals on the right. If one variable remains the same or not mentioned, leave it out of the equation, completely cross it out. So I'm going to do an example. A gas in a rigid container has a pressure of 3.5 atmospheres at 200 Kelvin. Calculate the pressure at 23 degrees Kelvin. So notice that it said a rigid container means the container can't change its volume like a balloon would, so we're going to cross the volumes out. We should also know that because pressure and temperature have a direct relationship, since our temperature went up, our pressure should go up, and that's a good check on your work when you're done. Our first pressure was 3.5 atmospheres, and our first temperature was 200 Kelvin. Our second pressure is unknown, where our temperature is 273 Kelvin. We're going to cross multiply and divide by 200, get x alone, and that means our answer in sig figs comes out to be 4.8 atmospheres. That confirms the pressure did increase. Now we're going to do it a little bit slower together. A 32.9 liter sample of a gas at constant pressure, that means that the pressures will cancel, increases in temperature from 25 to 45. You should be thinking, hey, volume and temperature also have a direct relationship. If the temperature is going up, the volume should go up. Technically, if the temperature goes up by almost double, the volume should go up by almost double. But keep in mind that's in Celsius, so we're going to have to convert that to Kelvin. So we know that the volume should increase. Let's calculate that new volume. The first volume was 32.9. The temperature is 25 plus 273, which is 298 Kelvin. The next volume is unknown, but the temperature should be 45 plus 273 to be 318. When you cross multiply and divide by 298 to get the x alone, our answer came out to be only 35.1 liters. It did go up, but didn't go up substantially because the Kelvin temperature didn't go up a lot. So the Kelvin temperature only crept up by a small amount. The volume can only creep up by a small amount. I want to see if you can do this. A 45 milliliter sample of a gas at standard pressure, notice standard pressure is on the front of your reference table, is heated from 20 to 50 degrees Celsius. The pressure of the gas is at 107.9 kilopascals. What's the new volume of the gas? Let's check to see if you did what you were supposed to do. Notice this one had all the numbers in it. So the pressure on table A is 101.3 kilopascals to match the 107.9 that was given. The volume was 45, and we need to be in Kelvin, so 20 plus 273 is 293, and then 50 plus 273 is 323. When you cross multiply, you have to multiply the three numbers that are in a row, 101.3, 45, and 323, and divide by the volumes, the temperatures and the pressures that were with the x. So divide by 107.9, and also divide by 293. Our answer came out to be, with sig figs, 47 milliliters. That shows that the volume went up slight bit. At this point, you should be able to convert your units to make sure they're matching and in Kelvin, so you can calculate the pressure, temperature, and volume of any gas.